For quite a while, people have envisioned what life might resemble in different universes. Because of the James Webb Space Telescope, the most impressive telescope in existence, that question can at last be answered. While observing the nearest star system to us, Proxima Centauri, which is just 4 light-years away, researchers have observed several exceptional irregularities from one of the planets in the system, Proxima B. These peculiarities, called artificial lights, have confused the best personalities in established researchers. However, what are they? Do these lights suggest the presence of wise life on the world? Join us as we explore James Webb's unnerving discovery of city lights that change everything. The main life that we are currently aware of is on Earth. Starting from the start of civilization, individuals have questioned whether there is life elsewhere in the universe. To do such an interstellar hunt, American cosmologists Jill Tarter and Thomas Pearson set off the search for Extraterrestrial Intelligence Project in 1984. The charity's objective is to gather spaceborne radio transmissions. Radio waves can travel farther and are therefore more likely to be detected by the 42 radio telescopes that make up the unique Allen Telescope Array in the Californian Cascade Mountains. Since they are less scattered or absorbed than other types of radiation, in the beyond 30 years, no evident alien transmission has been found. After that, the James Webb Space Telescope, progressing in its dispatch, boosted the journey to inspect a range of distances, unseen planets circling distant stars. The largest telescope in the world, which is floating approximately 1 million miles from Earth and equipped with extraordinarily sensitive detectors, will be used. Quite a while back, there were no known planets outside those in our local planet group. Yet, since then, more than 4,000 additional planets, also referred to as exoplanets, have been discovered orbiting other stars. According to NASA, the universe might contain trillions of exoplanets. The earliest signs of something going on under the surface beyond our planetary system might be found in extraterrestrial vegetation. The Galileo shuttle turned its equipment back toward Earth when it was on its way to Jupiter and found a distinct sign of the existence of vegetation. The instrument detected the vegetation red edge, a combination of red and infrared lights reflected by plants. For example, a planet like Earth that is covered in a jungle should have intense areas of strength for an easy-to-detect red edge. The JWST will measure the red edge of distant Earth-like planets in the habitable zone around stars. They could be significant indications of something going on under the surface in the exoplanet atmosphere. When sunlight crosses a planet star, the JWST might be able to detect it as it enters its atmosphere. The light's missing frequencies would then be found via spectroscopy. Atoms and molecules in the atmosphere absorb specific frequencies, creating a characteristic fingerprint that the JWST can recognize. This method could be used to determine the composition of the atmosphere and whether life is possible. Most likely, life could exist on Earth-sized planets with atmospheres like our own, with the predominance of oxygen, nitrogen, and carbon dioxide. Be wise searching for elements that aren't typically present. One might be able to identify industrial life. Chlorocarbon CFCs, produced for use in refrigeration and cleaning products, would probably be detectable to alien monitoring Earth's atmosphere from a distance. If the JWST found CFCs in planetary atmospheres, that would be a clear sign of civilization. Really, life on an exoplanet might not in any way look like life on Earth. In some cases, even natural life, like extremophile species, can seem alien. This is a group of animals, primarily bacteria, that can persevere in conditions where other living things would perish. Some can endure heat up to 250 degrees Fahrenheit, some can endure colds as low as -4 degrees Fahrenheit, and some of them can survive major areas of strength foreign with pH levels under 3, while others can be found on Earth where we wouldn't expect to find any life at all. Yet, since planets like Earth are more likely to support life than planets with extreme temperatures or acidic environments, it might be wise to start with those first. Prime candidates could have temperatures that allow liquid water to exist on their surfaces and orbit a stable star. The classification for our Sun is a yellow G-type star. These stars are rarer and typically have shorter lifespans in our universe. The likelihood of focusing on planets orbiting around red dwarf stars, which are more frequent and have lower luminosities and temperatures than the Sun, is higher. There is additional opportunity for the development of life and evolution to produce complex life forms because these stars have longer lifespans. Essentially, around 40 light-years from Earth, the TRAPPIST-1 planetary system will be the subject of JWST's first mission. It orbits around a quiet red dwarf star with 7 Earth-sized rocky planets. 3 of the rocky planets in the so-called habitable zone could have liquid water on their surfaces. The TRAPPIST-1 star, despite having a much smaller and colder mass than our Sun, emits light that is similar to that of Earth. Due to the close orbit of its planets, the most likely chance so that people might see city lights outside the planetary group is Proxima Centauri, a red dwarf star that is 4.25 light-years from the Sun and our nearest star. Proxima is times fainter than the Sun, so a planet should be times closer to it than Earth is to the Sun for it to support life due to liquid water. In August 2016, cosmologists found a planet with 1.3 times the mass in this habitable region. In a Goldilocks-like habitable zone where the light intensity is perfect to melt water, Proxima B orbits Proxima Centauri. It's possible that Proxima B is an airless dead planet, given that it orbits its red dwarf star, Proxima Centauri, at a distance of just 46 million miles. The planet Proxima B is in a close orbit that exposes it to strong solar winds that can completely destroy its atmosphere. It also provides ample sunlight for temperatures and liquid water that are similar to those on Earth. Because of its proximity to the star, Proxima B is believed to be tidally locked, continuously showing the same side to the star as the Moon truly does concerning Earth. Proxima Centauri is around 18% the mass of the Sun and emits undeniably less brightly than one could expect for a planet so close to its star, 5% of the world's sun distance, which might be expected to be a red-hot spot. Fluid water could easily exist on Proxima B as long as the planet has an atmosphere to warm it, since the total energy reaching it from the Sun is only 65% of what Earth gets. However, the planet isn't particularly hospitable to life. It is most likely tidally locked, which means that it always faces the same direction toward the star and produces very stable, constantly favors large temperature changes. The planet also receives 100 times the high-energy radiation as Earth does due to its proximity to Proxima Centauri, including X-rays and bright lights. Proxima B is also bombarded with high-energy particles during star flare-ups. Unless it has a protective magnetic field like Earth, however, there are certain plausible scenarios that could make it a habitable world. Unfortunately, models suggest that the atmosphere of tidally locked planets might be prone to a rapid breakdown due to the freezing out of volatile gases on the night side. A planet's atmosphere can be replenished by volcanic activity, and for planets with strong magnetic fields, this atmosphere is less likely to escape. Since we know nothing about Proxima B's volcanic activity or magnetic field strength, we couldn't accurately predict whether the planet has an atmosphere. Yet, since an atmosphere implies the presence of seas, and the two taken together imply the existence of life, we are eager to know. On the off chance that Proxima B has a developed civilization, it could have solar chargers covering the day side to generate electricity to light and warm the night side, which would otherwise be too cold and dark for comfortable habitation. The discovery of Proxima B has sparked a race to determine if it transits its star's face as seen from Earth. These transits would allow scientists to determine the planet's size and mass, which would then enable them to determine its density, knowing that would validate the planet's rocky makeup and provide information on the materials used to make those rocks. During a transit, starlight could reveal the nature of the planet by passing through its atmosphere, but the likelihood that the orbit will be in the correct alignment, so that scientists can observe a transit, is only 15%. The star's propensity to erupt also complicates matters. Astronomer David Kipping of Columbia University says the star is deceiving, as star's heat makes a rocky planet absorb sunlight and emit it as infrared light. However, rocky planets emit a distinct type of infrared radiation from stars like Proxima and Earth. Furthermore, the James Webb Space Telescope was made specifically to focus on infrared light. Proxima B's infrared intensity signature is the key to detecting the planet's atmosphere. Moreover, the infrared portion of the spectrum has signatures for water. The JWST will be able to detect city lights on Proxima B's night side, even if they were just as faint as what our civilization currently uses on the night side of Earth. We could detect artificial illumination for as long as it was confined to a frequency band that is 10 times narrower than the starlight. Proxima B's day side is heavily covered with solar chargers due to its unique spectral edge's ability to reflect starlight. As Proxima B orbits around its star 24/7, cool night lows follow daytime highs. The difference in temperature between day and night, however, depends on whether the planet is entirely made up of bare rock. Because an atmosphere and ocean both moderate temperature overall, if there isn't an atmosphere, Proxima B's dayside and nightside temperatures will vary more. In fact, since the dayside will radiate all the energy it receives from Proxima Centauri as a dark body, we can calculate the exact amount of dark body radiation that should be present on the night side. On the other hand, the night side will appear to be a frozen wasteland. If the temperature difference between day and night is less pronounced, we can infer the presence of an atmosphere. Conveniently, assuming the dayside and nightside temperatures differ, it will only take the JWST 101 Earth days to measure the radiation from Proxima's two faces after it has completed its orbit around the star. If Proxima B has an atmosphere, the next step will be to analyze its composition. The presence of gases like oxygen, water vapor, and methane, in particular, could indicate the presence of habitable conditions if not actual living things. To achieve this, however, we must successfully capture starlight as it bounces off or passes through the planet's atmosphere, which is a truly challenging task. Nevertheless, Webb can closely examine a few of the nearest potentially habitable worlds. Since it was not built to search for extraterrestrial life, and it is limited to tracking changes in the atmospheric concentrations of methane, carbon dioxide, and water vapor, Webb cannot detect the presence of free oxygen, which is the strongest sign of something going on under the surface. Even if some combinations of these gases may be reminiscent of life, one must have a thorough understanding of a planet of interest to assess if its geologic or atmospheric processes potentially resemble a biosignature and help to rule out false positives. The next wave of exoplanet exploration may produce the undeniable evidence needed to outline the reality of life. The James Webb Space Telescope's preliminary data provides us with a glimpse of the significant advancements to come. If there is life elsewhere in the universe, it is one of science's most pressing questions. Is it possible that life is abundant throughout the universe? Or is it also possible that we are completely alone and trapped on a singular planet in deep space? Regardless, significant philosophical and psychological shifts among people will likely be necessary for the eventual resolution. For an extensive period, humans have embraced fantastical notions about the possible existence of life on distant celestial bodies. These ideas, fueled by scientific inquiry and speculative fiction alike, have long captivated the human imagination. But it was only after the advent of remarkable technological marvels, such as the James Webb Space Telescope, JWST, that the tantalizing prospect of uncovering such extraterrestrial secrets became more than mere speculation. The JWST stands as a testament to human ingenuity, representing the zenith of observational capability with its unparalleled abilities. It promises to revolutionize how we may perceive the universe, allowing us to peer farther into the cosmos than ever before. Armed with this technological marvel, scientists turn their gaze to the nearest star system to our own, Proxima Centauri, located a mere 4 light-years away. This celestial neighbor entices with the allure of discovery. Within the Proxima Centauri system lies Proxima B, a planet shrouded in mystery and intrigue. It is here that scientists have detected anomalous peculiarities, artificial lights, casting doubt on the conventional wisdom of a barren, lifeless expanse. These enigmatic illuminations have confounded even the brightest minds within mainstream science, sparking intense speculation about their origins and implications. Could these artificial lights ever be heralds of intelligent life lurking amidst the cosmic void? The very notion sends shockwaves through the scientific establishment, challenging long-held assumptions about humanity's place in the universe. As researchers grapple with this profound question, the JWST stands poised to unravel the mysteries of Proxima B, offering glimpses into the unknown and potentially reshaping how we perceive life's boundless prevalence. Yet, the quest for extraterrestrial intelligence extends far beyond the confines of our cosmic backyard. Since time immemorial, humans have looked skyward, pondering the existence of cosmic companions. This quest for celestial companionship found renewed vigor with the inception of the search for extraterrestrial intelligence, SETI, project, led by visionary astronomers Jill Tarter and Tom Pearson in 1984. Armed with an array of cutting-edge technologies, SETI embarked on efforts to scour the universe for signs of intelligent life, harnessing the power of radio telescopes to sift through the vast expanse of space in search of elusive transmissions. Yet, despite decades of vigorous effort, the deafening silence persists, leaving humanity to confront the daunting possibility of its solitude in the cosmos. Enter the JWST, a sentinel of humanity's insatiable curiosity, poised to pierce the veil of cosmic anonymity and shed light on the